Good morning. Today we're going to talk about hybrid systems. So far in the course, we have considered individual domains. We analyze the different elements in each domain, except for the case of the flexible container that we had a fluid system, the fluid capacitor, and then we had the container itself that was modeled as a spring. So the concept here in this section of chapter 2 is to find or understand the links that we're going to use to connect the different domains. So I define those as hybrid systems. So hybrid in the sense that there are going to be multiple domains that are going to be interconnected. We're going to consider the case, for example, of an electric DC motor. And in an electric DC motor, we're going to have the electrical domain, which is going to be our electrical circuit, where we're going to have an input voltage. And then on the other side, we're going to have the rotor of the motor, which is going to be a rotational mechanical system. Now, the through variable for the rotational mechanical system is torque, and the cross variable is angular velocity, whereas for the electrical circuit, we have current and voltage. Now, the relationships that we're going to have are as follows. For the torque, we're going to have that the torque being applied at the rotor of the motor is going to be equal to Km, where Km is a constant, is related to the motor torque, times the current. And the current is the current of the armature that we have in our circuit. And the motor itself, it would work as a generator. So there is going to be a back EMF or electromotive force voltage that is being produced. And this is going to work against the input voltage source. And the relationship that we're going to have of this voltage EMF is going to be with respect to the angular velocity of the rotor. And the definition is that the voltage EMF is going to be equal to the back EMF constant, K EMF, times the angular velocity of the rotor. So for an ideal electric DC motor, we're going to use these two relationships. Now, the word ideal is that perhaps you can define the relationship in a different way that is not going to be nonlinear. It is possible to represent it as a nonlinear relationship, and that would make it more complicated. But for the moment, we're going to consider that the links that we're going to have between the electrical and mechanical domains is going to be in a linear form. Other examples is, for example, a potentiometer, and we can have either a translational or a rotational. The translational is a slide pot, and the rotational thumb pot, where you have a knob. And here it's basically an input voltage, and here we have a resistor. And it's a variable resistor that we can change. So we have this slide pot that we can, or the wiper of the pot that we can change. So if we put it at the very top, so the input voltage is going to be equal to the output voltage. So based on this relationship, X is going to be equal to X max. So the two numerator and denominator are going to be X max. So they cancel out, and we have that the input voltage and the output voltage are the same. But if you lower the wiper, then the voltage passing through this resistor will drop, and depending on the value of X, we're going to have a different output voltage. So the output voltage is going to be the ratio of the X, the position of the wiper, divided by the maximum length of the resistor times the input voltage. And for the rotational pod, we have exactly the same thing. We're going to have a wiper that we can vary. We're going to have a rotational resistance, and we can vary that from a maximum value of theta max, in which we're going to obtain that the voltage out is going to be equal to the voltage in. But as we reduce the value of theta, then the input voltage is going to pass through this resistor, and we can vary the output voltage. Another example is related to a hydraulic turbine. In a hydraulic turbine, we're going to have a fluid system where pressure and volume flow rate are our two state variables. And then we have the impeller or the turbine of the hydraulic turbine that is going to be our mechanical rotational system. Now, the relationship that we're going to have for this particular system is that the pressure is going to be equal to K1 times the torque, which is the torque that it's being applied to the impeller of the pump, and that K1 is a parameter that is defined in commercial pumps, and it's the volumetric parameter of the pump, and it's measured in CIPRs, which is in cubic inch per revolution. And the other relationship that we're going to have relates the angular velocity of the turbine with respect to the volume flow rate. And again, there is going to be a constant that is also constant that is defined by the pump itself, and the relationship is given here, which is the angular velocity of the impeller is going to be equal to this constant times the volume flow rate. So this is an example of a toy. This is I remember having one of these a long time ago when I was a child. And the way that it works is there is a small tray here in which you put a solid alcohol. It's like a white block like that, and you place it on the tray and light it up and put it under the tank, which is filled with water, well, to a certain level, and then you let it heat up until the water turns into steam, and it will pass through a small valve here, and you can see the pipe that will take the steam towards the cylinder, the piston of that we see here. And then eventually the pressure of the steam is going to build up, and it's going to move the piston, and then it's going to release, and you can see it in this example here. And as you move the piston is connected to a slider crank, so the crank will rotate a flywheel or a pulley, and it will turn around and the piston will back up. And again, the steam will go in again, and then there is a small valve in this example that opens and closes for the heat or for the steam to go in and out. And eventually the rotation of the flywheel can be connected to a belt or a chain that will take you to another pulley up here where you can have a small DC motor, a generator that can be used to light up to turn on a light bulb. So in this fairly simple example, we can see that we go through all the stages of the or all the domains that we have seen so far, from a thermal system to a fluid system to a mechanical translational to a mechanical rotational to an electrical system. So it's a toy, and it combines all the different domains, and there are going to be relationships between all of them. So it would go from, for example, the Gay-Lussac law will relate the change in pressure and temperature inside the tank. So that will give you the relationship that we would have between the temperature inside the tank with the pressure that is being built inside, that will eventually be taken in the fluid system towards the chamber of the piston. And then we would apply the concept of pressure and force. So there's going to be a relationship there that will produce the motion of the piston. And then as we turn, and I mean, there is going to be the relationship of the force that the piston is applying to the crank is going to be related to the moment or the torque that we're applying to the flywheel. And then the flywheel will be connected to a pulley, and the pulley would give you a torque that the torque will produce. It will be related to the armature current of the electric circuit, and eventually we're going to have a resistor that can model the light bulb. So you can see that there are many domains, and there is going to be a relationship between them, and we're in most of the cases we're going to consider a linear relationship that will allow us to make this connection between the domains. What we're going to do in the next couple of lectures, so that we have one on Friday and one on Wednesday, we're going to cover two examples. The first example, which I'm going to record, is about a domestic fan where we have a DC motor, which is our electrical system that will turn, and we have the fan, which is the mechanical rotational system. And we're going to develop the state model for that. I'm going to solve this problem, and I'm going to record it, and then there is no video that I'll be posting on Wednesday. Instead, we're going to solve the second problem, which is related to, I'm going to cover it in two parts. The first one is a fluid system. We're going to have a centrifugal pump, but we're just going to assume that the pressure of the pump is the one that is sucking the water from a well and taking the water towards this tank in the house. And later we're going to focus on the pump itself and how that one is going to be connected with the fluid system. So we're going to work on both of these problems separately, and then what we're going to do is we're going to combine them using the ideal equation for an ideal turbine. So we're going to do that, and we're going to establish what would be the state model for this particular problem. Okay, so let's solve the problem of the domestic fan. And in this case, we're going to have two different domains that are going to be coupled. We're going to have the DC motor, and then we're going to have the fan, which is our mechanical rotational system. So what we're going to do is we're going to establish the relationship between the two domains, and then we're going to focus on the electrical circuit, the way that we're going to model the DC motor, and then the way that we're going to model the fan. We're going to develop the constitutive equations, and we're going to eliminate some of the redundant variables that might appear, and eventually we're going to combine everything and develop the state model of the system. So we're going to start this problem by defining the relationship that will couple these two systems. And as we mentioned in the introduction of this section, we're going to have that the torque that is being applied to the rotor of, well, in this case, the rotor or the of the motor, which is an inertia element, is going to be equal to the a constant Km times the armature current. Okay, and we're going to define that as equation number 1. The other equation that we're going to need to couple the two systems is the one related to the voltage, the EMF, the EMF voltage, which is the rotor, the rotating motor is going to generate this voltage. And this is going to be equal to the constant K EMF times the angular velocity of the rotor. And I called M for motor, which is the rotor of the mechanical part of the DC motor. And that would be the second equation. Okay, so now what we're going to do is we're going to create our circuit for the DC motor, and we're going to have our input voltage that we're going to call just V of t, and this is going to be positive, negative. We're going to go through a resistor, and then we're going to go through an inductor, and then we're going to go where we're going to have the motor, and we're going to close the circuit. Okay, so we're going to define that RA. This is going to be our LA, the inductor, and then here we're going to have the voltage EMF that is going to work against. So this is positive, negative, positive, negative, the source voltage. And this is the current of the armature will be defined as IA. Okay, and we already know the resistance, the inductance, and here we're going to define VEMF. Okay, then let's look at the fan itself. The fan, we're going to have our rotor, and the rotor is an inertia element, and we're going to so let's define that as JM, and there is going to be an input torque, and that's a torque that is coming from the electric circuit, and that's tau M, and we're going to assume that there is some friction, and that is a constant B theta M, and that's based on the motor. Then we're going to consider a flexible shaft, and the idea is that as you start applying the voltage, then that flexible shaft would start twisting, and at some point it will build enough torque that will allow to move the fans. That's just the way that we're going to model it. If we were going to model it with a rigid body, then all these would be a single element. But we're going to assume that there is a flexible shaft that we're using to build that torque in order to start moving the blades of the fan. So we're going to have this flexible shaft, or a flexible shaft, and then we're going to have another inertia element that represents the blades of the fan. Let's call that JF. And then there is going to be some friction due to the blades that are moving in a fluid, which is basically the air. So we're going to assume a second friction here that is going to be B theta F. Okay, so now we developed all the components that we're going to use for our model. So we can count, first of all, the number of energy storage elements that we have. So we'll have a better idea of what is the order of the system and what would be the size of the matrices at the end. So we have, this is an input, then we have dissipating element, then we have the inductor, which is an energy storage element. So there is going to be one. Then we go with an inertia element, which is also an energy storage. And then there is friction, which is not, it's a dissipating. Then we have flexible shaft, which is, in this case, would be number 3. And then we have another inertia element that would be number 4, and then friction. So we have, and let's just label them 1, 2, 3, and 4. So these are the 4 energy storage elements. So this is a 4th order system. Eventually we're going to get an A matrix that is going to be 4 by 4. So now all of them are independent. There is no dependency among them. And as I mentioned before, if that was a rigid link, then we would have the whole system here would be just a single inertia element. So at the end, it would be a 2-order system instead. So the state variables that we're going to have, I'm just going to write them in green. We're going to have the current of the armature. So it's going to be, I define that as IA. Then we're going to have the inertia element, and the inertia element for the motor or the rotor of the motor is the state variable associated to an inertia element is angular velocity. So it's going to be omega m. Then we're going to have the state variable associated with the flexible shaft, and that would be tau k. And finally, we're going to have the state variable associated with the other inertia element, and that would be omega f. Okay, so these are going to be eventually our 4 state variables. So the next step would be to start developing our or defining our equations. So I'm going to look at the electric circuit first and define some relationships. So we're going to have the continuity relation. And remember, continuity relation is related to through variables. So in this case would be currents, and in the case of the circuit would be Kirchhoff's current law, okay, KCL. And in this case, the current passing through the resistor, this is our node here, is going to be the same as the current passing through the inductor, which is our armature current at the end. So we have that IL is going to be equal to IR, which is going to be equal to IA. And that IA is eventually what we have here as the variable that will allow us to link the mechanical with the electrical system. The other equation is going to be related to the compatibility. Relation. And that is going to be KVL, Kirchhoff's voltage law. And that is going to be the sum of all the voltages around this loop must be equal to 0. So we're going to have that the voltage, the input voltage is going to be equal to the voltage at the resistor plus the voltage at the inductor plus the EMF voltage. Okay, so let's label these ones as equation 3 and equation 4. Okay, let me just grab another piece of paper before I run out of space. And we're going to define the constitutive equations now. So we have the electrical system. So the constitutive equations are for the inductor, we have LA times the time derivative of the current is going to be equal to VL. Okay, and then for the resistor, we're going to have, I was using blue, that VR is going to be equal to I define it as RA times IR. Okay, and this is going to be equation 5 and 6. Actually, what I'm going to do is I'm going to, let's call it 5 and 6. Okay, what we're going to do is VL is not one of the state variables, but we have VL here, so we're going to substitute this equation in here, and eventually we're going to come up with VR, and VR can be substituted from here. And after we make the substitutions, we're also going to substitute the continuity relation and write everything in terms of IA, okay, which is one of the state variables. So substitute equation 4 in 5. So we're going to get LA DIL dt. I should have used blue, but okay. It's going to be equal to VT minus VR minus VEMF. And now we're going to substitute 6. I'll now use blue. LA and I'm also and equation 3, which is just the relationship of the current. So now it's everything in terms of the armature current. It's going to be equal to VT minus RA times IR, but IR is IA, minus VEMF. Okay, and then eventually VMF, we're going to substitute this relationship that we have here. Okay, we can, well, write that actually. We can just do the sub is equation 2. Going to be 1 over LA that multiplies and now that is KEMF times omega m. And what we're going to do is make sure that, and I'm just going to bring in the state variables that we defined from the 4 energy storage elements. And we have to make sure that our equations, eventually these are going to be our state equations, are going to be written in terms of inputs or state variables. So we have an input. Here we have, these are coefficients, so that's okay. Then we have the current, the armature current, which is one of the state variables. And then we have omega m, which is another state variable. So now this is going to be one of the state equations that we need. So we'll define that as equation 7. This is going to be one of the state equations. So now we look into the mechanical system. Just going to fold the page, sure. Might be able to do everything. So we no, it's too small. Okay, so that was our mechanical system. So we're going to analyze each element, and we're going to start with the first inertia element. So and this is Jm. So this is the inertia of the rotor. So our input is going to be this torque tau m, and this is the one that is being applied, and we're going to assume that the inertia element wasn't moving. It was in this at rest, and as we start applying, then the inertia element is going to be turning in the direction of the torque. Now, what are the torques that are trying to stop this torque, like counteracting? We're going to have the torque coming from friction. So friction is trying to counteract that. So it's going to be tau, we define it as B theta m. Then we're going to have also the rotational spring or the flexible shaft that is also acting against this torque, and this is going to be tau k theta or tau k. That's how we define this variable. And we're also going to have the inertial moment, which is going to be Jm. Let me just do it on the side, otherwise I won't have space to do all of them. So this is going to be Jm times the time derivative of omega m with respect to time. Okay? So if we, and again, we consider that the system was at rest. That means that through the rotational spring or flexible shaft, we're going to have that theta m, so the rotation that we're going to have in this inertial element is going to be greater than the theta from the blades. And this is because the other rotation is going to be the torsion along the flexible shaft. So based on that, we can create now our constitutive equation using Newton's second law. So Jm times the time derivative of omega m is going to be equal to the input, which is tau m minus, now we're going to write all the tau b theta m minus tau k, and that would be equation, I believe it was 8. Okay, then we analyze friction, and I'm just going to write the constitutive equation for here. That's the friction that we had there, and the equation for a rotational element is going to be tau b theta m is going to be equal to this zero angular velocity here, and the angular velocity of the inertia element is omega m. So this is going to be b theta m, the coefficient of friction, times omega m. Okay, and that is equation number 9. Then we go into the rotational spring, and the rotational spring is we're going to have the effect of this inertia element on the spring, and then the resistance of the other inertia element. And the constitutive equation is, now we're going to have, if we apply Hooke's law, we're going to have tau k is going to be equal to the stiffness of that spring, which is k theta, times, and now it's going to be the torsion that we have in that shaft, and we're going to have two angular displacements, one with this inertia element and the other one with that one. And we know that theta m is going to be greater than theta f. So the total torsion that we're going to have along the torsional shaft or flexible shaft is going to be theta m minus theta f. So we can write that equation in terms of our across and through variables. So this is going to be d tau k dt is going to be equal to k theta times omega m minus omega f. Okay, and that is going to be equation 10. Then we go to the other inertia element, which is the one related to the blades. So we're going to have a torque here, and that torque is the torque at the end of the spring, which is this one here, right? So this is going to be tau k, and this is the through variable along the flexible shaft or torsional shaft, and this is going to be the torque that is being applied to the inertia element. And then we're going to have the torques that are counteracting that, which is going to be friction. So we're going to have tau b theta f, and then we're going to have also the inertial moment, or which is going to be jf, I believe, or jf times d omega f dt. Okay, so that leads to a constitutive equation of the form jf d omega f dt is going to be equal to tau k minus the friction torque, and that is equation 11. And finally we have the final friction here, and so I'm just going to do it. And that is going to be I'm using blue, tau b theta f is going to be equal to the damping coefficient times, in this case we have omega f. Okay, so that's the angular velocity difference between the two bodies. It's friction, there is a bearing or something. No, sorry, this is for the wind, so we're just doing it with respect to the inertial reference frame. So it's going to be just omega f. And so that would be equation 12. Okay, so now we have a bunch of equations and we have to put them all together and develop our state equations and eventually form our state model. So I'm going to grab another piece of paper and start working. State equations, we already developed the first one after we made some substitutions for the electrical system, which is this one here. So I'm just going to rewrite that. So state equations. So okay, and then what I'm going to also do is I'm going to write up here the state variables, so we remember what they are, and make sure that all the state equations will be either inputs or state variables. So Okay, so we know that the first one is correct. Then we're going to go and do the second one. So what we're going to do is we go to our first inertia element, which is this one here. And here we have tau m. Now, tau m is not one of the state variables. Then we have tau b theta m, which is also not one of the state variables. And then we have tau k, which is one of the state variables. So we have to find the relationships that we would have to introduce here in order to convert them into terms that contain state variables. So the friction torque is going to be this relationship that is going to be a function of omega m, and omega m is one of the state variables. And what about the other one, tau m? Where do we have tau m? Well, tau m comes from the first equation. That's the equation that will allow us to couple the two systems. So tau m equals km IA, where IA, the current of the armature, is one of the state variables. Okay, so we're going to do omega. So the time derivative of the angular velocity is going to be equal to 1 over m that multiplies tau m, and again tau m is km IA. Okay, km IA minus, and I'm just going to write in green, this is from equation 1. Then we have, so that was equation 7, just to keep, that was equation 8, where we're taking this equation, minus the friction torque, and the friction torque is b theta m omega m, and that was equation 9 that we substituted here. And then we have minus tau k. Okay? And now we have everything written in terms of state variables. Then we go and look at this equation, which is the one related to the torsional spring. So this is going to be equation 10, another differential. And we can see that it's already written in terms of omega m and omega f, and both of them are state variables. So the tau k dt is going to be equal to k theta that multiplies omega m minus omega f. Okay, and the last state equation is going to come from the Newton's second law for the other inertia element. So this is going to be equation from equation 11. And what we have is d omega f dt. Okay, just have to push it a little bit higher. It's going to be equal to 1 over jf that multiplies. So we have tau k, and tau k is one of the state variables, so that's fine. And then we have minus tau b theta f, and that is the friction, and that comes from equation 12, so we can substitute that, b theta f omega f, and that came from equation 12. Okay, so now we have all the state equations, so now we can create our state model with the state equations. So we're going to write and our input is going to be the input voltage. Okay, and so this is here, we're going to have the input voltage. Okay, so we start with equation 1. So I should also write the state vector. Okay, so equation 1, we have, or the first state equation is going to be 1 over LA that multiplies the input. Now let me just see if, yeah, sorry. 1 over LA that multiplies the input vector, voltage, and then we have minus RA times IA, so it's going to be minus RA divided by LA, right? And then we have omega m, which is the second one. So this is going to be minus K EMF over LA. And then we have 0 and 0. Okay? Then we have the second equation, that is this one here. And we have 1 over Jm that multiplies Km times the current. So it's Km over Jm. And then omega m, we have minus B theta m over Jm. And then we have the torque at the flexible shaft, which is minus 1 over Jm, and then that would be 0. And then that one is also 0. And then for the next one, we have K theta times omega m, so that's K theta here, and then 0 and minus K theta that multiplies omega f. And the last one is 1 over Jf times tau k, so that's here 1 over Jf, this is 0, 0, and then we have minus B theta f over Jf that multiplies omega f, and then these ones here should be also equal to 0. And with that we conclude the model. So you can I don't know, in this case perhaps what we're interested in is the angular velocity of the fans. That could be our output. So the solution, if you wanted to get it, it would be, let's assume that that's our goal. We're going to have our state vector here. So this is just going to be 0, 0, 0, 1, and then we have 0 times Vt. Okay, so this is just kind of what would be an output on its own. So this is the state model of the form X dot equals AX plus BU, and then the output would be y equals cx plus du. Okay, you can have other outputs. Perhaps you're interested in the angular displacement, so you would have to go back and use that equation, and eventually you would have you would relate what would be the displacements, but in this case would make more sense to determine the RPMs of the blades. So that would be the example of the domestic fan, and we had a hybrid system, an electrical circuit combined with the physical fan with the rotor and the blades, and we developed our state model, which is represented by that equation.